view. Can you hear me? Okay, so I already asked Saifu to send you the data set already. So today we'll be using this data set, which is actually the diabetes data set. It actually comes from this paper in 1997. So you can go and look up this paper on PubMed. Just look up for this PubMed ID 9258308. Okay. So it's actually looking at smoking and cholesterol in in various populations. All right. So the first thing that you have is when you encounter a large data set, okay, because it's actually quite big. I think there are 398. Some places they use 403, but somehow my last few rows gone missing. But it doesn't matter. You have to you have to note what are all the variables. Okay, so ID is ID of the patients, cholesterol is the cholesterol level, stable glucose level, HDL is the high density lipoprotein ratio. I can't remember, so you have to go and look it up. Glycosylated hemoglobin is what's the basically this is the measure of diabetes. So when glycosylated hemoglobin goes above 7, this is when a person is diabetic. Location, where the person lives. There's only 2 locations, your Buckingham and Louisa. Age of the patient, male or female. Height and weight. Height and weight is actually in inches, not in centimeters. Okay. So the measurements are actually in inches. The frame. So this talks about body frame, small, medium, or large. Then you have blood pressure. Okay. The first measurement of blood pressure, your systolic blood pressure and diastolic blood pressure. So this you should know what is systolic blood pressure, what is diastolic blood pressure. Okay. So sometimes if you go to a doctor to measure blood pressure, especially if it's a bit high, you will be asked to relax a bit, go out and wait. So half an hour later or 15 minutes later, you come back for the second measurement. So some patients will have the second blood pressure measurement. This is the waist and hip in inches. This time I'm not actually sure what it is as well. So that's not a problem. Okay. So we are using this data set to kind of play around to go through some of the statistics. So in order to do statistics for Excel, to make yourself easier, you should have this thing known as, under your data ribbon, you should see this thing known as data analysis. Okay. So this data analysis toolkit. If you do not have, then you go to file, okay, click on more, go to options, then go to add-ins, click on this manage Excel add-ins, go, and then you highlight analysis toolpack VBA. Okay, that will give you this analysis toolkit. Okay, so we'll be using this for as much analysis as possible. Now, for example, let us just take the age. Okay, just grab the age. So I just copy the whole column and I go to another sheet. Okay. So the first thing that I want to find out is maybe I want to do a summary statistics, a descriptive statistics. What is the mean, median, all this different stuff. Okay. So I can actually do it using the formula. So I can find out what is the average age, median of the age, and so on, the standard deviation of the age, using a formula as well. So if I use a formula, you also should learn how to use formula. Average is average. You highlight the whole column. You find out what is the average age, which is about 47 years old. median, there are two ways. One is to use median. So the median age is 45 years old. Another way is to use this thing known as quartile. Use a quartile include the array. Then the second variable asks you what quartile. 0, if it's 0, it means it's a minimum value. 1 is the first quartile, 2 is the median, which is the 50th percentile. 3 is the third quartile, so you can use 2. Okay, so that is, you can find quartile as well. Now, standard deviation, there's also two versions. Use standard deviation .s. Okay, that is a sample standard deviation. .p is the population standard deviation. Okay, so that is your standard deviation. Okay, another way that you can do your summary statistics is go to your data analysis tools and look for this known as descriptive statistics. So basically, I'm just showing you. I'm not expecting you to follow as I go along. If you want to follow, then after this whole lecture tonight or whatever, go through yourself. Okay, look at the lecture, stop, and go through yourself. Okay, so input range. Input range, I will have the whole column A, and it's grouped by column. So I also have the labels. The label is actually in the first row, so I've got to tick it. The label in the first row. And I want to display the output range, the output value in column F. So what do I want to display? I want to display the summary statistics. Okay. For example, I also want to display the 95% confidence interval as well. So these two. So I just click OK. You will display the statistics for me. So I got the mean, the standard error, the median mode, standard deviation, sample variance. Sample variance simply is the square of standard deviation. So kurtosis and skew, you do not really need to know about it. The range, okay, range is actually minimum minus maximum minus minimum, the sum, the count, and so on. So the 95% confidence interval is of the mean. 95% confidence interval of the mean is 1.6. So it's 1.62. It's actually 46.9, the mean plus minus this number. Okay, so that is how you can do it. Now, there's actually one more thing that you can do in this data analysis step, which is quite useful. Most of the time you want to plot a histogram, but this histogram function is actually pretty hard to use, pretty difficult to use. So normally I will not do it. Okay, so how do I plot histogram? Okay, let me just leave it as is. So to plot histogram, I will need to have my bins first. My bins and my frequency. Okay. So since my minimum age is 19, okay, so I may want to decide that my bin is less than 20. So I can go 20 to maybe 20 to 29.9, 30 to 39.9, 40 to 49.9, 50 to 9.9, and so on. See, 9.9. Then I have the last one is more than 90. Okay. Now, when you do histogram, or make sure that the two bins do not overlap. Okay. So how do we calculate frequency? Okay. We use this function known as count if. It's a range. So you count if the criteria is less than 20. Count if his criteria is less than 20. That's it. So basically that tells you that there are two less than 20. So you can do the same. All right. In fact, this itself, let's insert a space. This we can use it, you can call it as your cumulative frequency. Okay. So if I just drag down the rows, I have to change in division number. Okay, so it's less than 20. So here I put less than 30, less than 40, less than 50, less than 70, less than 80, and less than 90. Okay, so here, since 99, I've just put less than 100. Okay. So this cumulative frequency means that I can use it to calculate my. So the first bin is itself. Okay. The second bin, you just take the cumulative frequency minus of what? The cumulative frequency before it. Okay, that's it. Then you just have it. This is your frequency that you want to calculate. Okay, and then what you can do is you can use here to plot your histogram. So you use a 2D plot. Now this is your put one side. Oops. Okay, so this is your frequency. Okay. So you realize that you can change a lot of different things. First thing that you have to do is go to add data. Now horizontal axis, you want the bits, so you just click on it, select the bits. Okay. Right. So you can add your chart title. Let's say I don't bother about chart title. I don't bother about my, oops, I need my axis. I don't want the grid lines. I actually hate the grid lines. Okay. Then what I need is I need my chart axis. Okay, so I have my chart axis. So I can label this as frequency. And here is my okay. Sometimes you realize that it's actually not easy to read, especially if the bins are quite close together. That means the words may be overlapping. That is not a problem. You can go to text option, format axis. Okay, click on format axis, format axis. Under this text option, you see this thing called alignment, size and properties. Okay. Here, what you can do is you can either change, swap it to this side, which is quite useful. But it's actually a bit can be problematic. Or you can just tilt. Use a custom angle and just tilt it. So you tilt to about minus 45 degrees. That should be quite nice already. Okay. But this is a bar graph, it's not a histogram. The difference between bar graph and histogram is a histogram has no space. Okay, so how do you remove the space? Quite easily, you go to this axis options. I think no, not axis options. Let's see. Okay. So you go back, you highlight the series, you do a right click and format data series. Okay. Format data series, what you need is you remove the gaps, change the gap from to 0. Okay, and it looks almost like histogram, just that now you need to put in the borders. The origin doesn't have a border, so you have to put in a black border. Okay, solid line, and that is your histogram. You can even change individual bar colors if you want. So that you highlight everything, you can change the fill. You can change it to a different color. Okay. I actually dislike the native color of Excel. Or you can even change individual color. So you highlight, I'm not highlighting only one cell, one block. I can change it to a different color. Okay. Similarly, you can also add your data labels. Add your data labels. So there are a few ways of doing it as well. Okay, and then you can format your data labels also. You can change the angles. Okay, you can change it. Okay, you can also align it differently. Okay, where's my alignment? Okay, let's go back to normal. Then you can change the position of it. Yeah, you can align it, you know, to the center of the cell of the bar. Okay, go to the inside of the bar and in the base or whatever. There are a few positions they can label. So it depends on which one is suitable for you. Okay, so that is your histogram. So summary statistics is actually quite simple to use. Next, we want to do your t-test. Okay, and if you realize that, let's say we want to look at, okay, does the cholesterol average is that? So let me just find a hypothesis. Okay, let me see. Let's say that my research question is this: is the average cholesterol in males equals to the average cholesterol in females. So in this case, I will do my so my null hypothesis is that the average cholesterol of males is equals to the average cholesterol in females. Okay. My alternate hypothesis is that the average cholesterol of males is not equals to the average cholesterol of females. Okay. So this is my hypothesis. Now, in order to do that, what I need is I need the cholesterol and the gender. Yeah. Copy. Sheet number 2, and I paste here. Oops, I paste it. So what I need is I need to arrange them so that I have the female in one column and the male in another column. Now, Excel is actually a bad statistical tool, but it is a tool that seems a lot of us have, so that's why we tend to use Excel. Actually, Excel is a very poor statistical tool. Okay, it teaches you all the wrong statistical methods. So how do we do that? You can copy female into here, male into here, and all this, but it's going to be very troublesome. So let's do a faster way. Go to your data ribbon, sort. We just sort by gender. Okay. So sort by gender, your female will pop up first because alphabetically female comes up first. So you just copy the females. In fact, just make sure that you just cut the whole female section, put it into females, then cut out the males. Go and put on the male section. Then you delete. Okay, so let's go to our data analysis tab again. You realize that if you go to Ttest, there's actually two sample Ttest assuming equal variance or assuming unequal variance. Okay, so there are two versions to use, either equal variance or unequal variance. So which one should you use? Is whether can you assume the variances to be equal or not. Okay, so you actually, in order to do this, we have a side test we need to do. Are the variances equal? Now hypothesis, variance of female the hypothesis is variance of female not equals to variance of males. So Excel, we have a test to do that. It's called Ttest for two sample for variances. Okay. So you click on that. Now data one range, input one range, you highlight the female. Input two range, you highlight the males. Okay. Then labels, you click on the labels. Okay. Because we highlight the labels as well. So output range, just go to the empty cell here, then click OK. Now, the first thing that you need to note is the F statistic more than 1? So basically what it does is taking the female variance divided by male variance. Okay, but because F distribution is not symmetrical, so I always tend to say that the F statistic should be more than 1. So I should flip the male and female. So let's do that. So I'm just reversing it. Okay. So I'm just flipping the numerator and denominator. Okay. So now it's actually this divided by this to give you this. Okay. Now this is the p-value. So there is 27.7% chance that the null hypothesis may be true. Therefore, we can assume that we cannot reject null hypothesis. Okay, we will say something like this: since the p-value is more than 0.05, we fail to reject the null hypothesis. To reject null hypothesis, we accept a null hypothesis. Therefore, the variances can be assumed to be equal. So now we actually do the actual test for this. So we use the Ttest assuming equal variance because we assume to be equal. Okay. So the same method, you click on the female as your showing true female and males. Hypothesize mean difference, don't bother. Okay. Click on the labels because we highlighted labels as well, and the output range. Say we put here. Okay. And then this is your results. Okay, this is your results. Now, if it's a two-tailed test, you realize that you see the mean is actually very similar. Okay, is actually not significant as well because there's about 68%, 69% chance that the null hypothesis may be true. So same thing, you fail to reject null hypothesis. Okay, and what does it mean? It means that the average cholesterol of males can be there's no difference to the average for females. All right. So that's how you do your t-test. Okay. So far, any questions? Any problems? Okay, when do you use t-test? When do you use ANOVA? Anyone? This is something that in your practical skills should be mentioned already. When do you use t-test? When should you use ANOVA?
Ttest is a comparison between two groups. ANOVA is more than two groups.
More than two groups. Okay. Yes, to some extent it's correct. But can we use ANOVA for two groups? Is it wrong to use ANOVA for two groups? Okay, let's try. Can we use ANOVA for this? Okay. So ANOVA, you also have the single factor ANOVA here. Okay. The two factor ANOVA is not easy to use. Okay. Excel is only quite useful for single factor ANOVA, which means one-way ANOVA. So let's try. Now, because ANOVA you can use for multiple groups. So let's say you have two groups, so you just highlight. And the groups is by columns. Okay. Data in the first row, the label in the first row. And let's look at the results. Input range, we put it here. Okay, generate ANOVA table for us. We just reduce this and I show you. Okay. What did you realize? Okay. When you use ANOVA for two groups, it is equal to t-test with equal variance. Because why? This value is identical. The p-value is identical. Okay. And what you realize is the F statistic is the square of t statistic. So you take this, if I square this, that means it is S statistic. Okay. So actually you can use ANOVA for two samples. One-way ANOVA for two samples is equivalent t-test assuming variance. It gives you identical results. All right. Because ANOVA doesn't have equal variance or equal variance, it assumes equal variance. Okay, so you can actually use ANOVA as well. Assume that if your variances can be equal. Okay, so this is an important part. It is possible. Okay. All right. Okay, so far any problems? Okay. Let's say, let's say you do another test which uses your PET T-test. Okay. For example, we want to ask a question or research question. Let's say, let's say you go out after you do the first systolic, the blood pressure, you go out to rest. Okay. So is there a difference between the two readings? Okay. Okay, your question will be this. Is there a difference between the first and second systolic blood pressure readings? So that's a that's a question. Okay. And your now hypothesis is there's no difference. Hypothesis is basically there isn't. So we are talking about systolic blood pressure. Okay, let's pressure 1S and BB2S. Copy this, screw out. What happened to my now you realize that there's actually a lot of patients with only one blood pressure reading. So I have to probably remove them. Okay. I would not want to remove it one at a time. So what I will do is I will just highlight the two columns, go to data, sort, and now I sort based on the second systolic blood pressure from largest to smallest. So when I sorted, I go to the end of the second blood pressure, and then this is where only the first blood pressure. I think delete it. So I'm done with it. Okay. So the next step I'm doing is there a difference? Okay. So I'm using the data analysis tab, data analysis, and I choose this test known as Ttest, add 2 samples for means. Okay. So I click OK. One range, and there are two range because I highlight the labels as well. So I click on the labels, upper range, alpha is by default 0.05. So the range I put at E5. So click OK. Okay, so this is the result. All right. Now this is the two-tail p-value. So is there a difference? Okay, fundamentally, since the p-value is less than 0.05, you actually reject the null hypothesis. You accept the alternate hypothesis. Means that there is a difference between the first and second systolic blood pressure reading. Okay. So actually, how does PET T-test work? PET T-test essentially, you create another column called difference. Difference is one minus the other. Then what I'm trying to say is the average of the difference equals to 0? And if the average of the difference, if the mean of the difference equals to 0, then there's no difference between the systolic and diastolic, the the two readings. If the average is not equal to 0, then there is a difference. So your paired t-test is actually a one samples t-test. So how do you do a one samples t-test? Okay. In this case, what we are looking at is, basically the research question is the same. Is there a difference? That means the research question is identical. My null hypothesis is average of difference equals to 0. My alternate hypothesis is the average of difference is not equals to 0. It is not average of difference is not equal to 0 means that there's a difference. It's the same way of writing. Okay. So how do you do a one sample test in Excel? There's no clever way to do it. You have to use an unclever way to trick Excel to do it. In order to do this, what you need is you need a dummy variable. The dummy variable is just 0. Just put everything in 0. Okay. Okay, let me just insert. Okay. All right, then what do you do? Because the variance of difference and the variance of dummy is going to be very different. Okay, so what you can do is you use t-test assume unequal variance. Because definitely the variance of this difference column and the variance of dummy column is going to be very different. Okay, so you use t-test assuming unequal variance. Then variable 1 range, you take the difference. Variable 2 range, you take the dummy. Okay. Okay, click on labels and let's see the output range. Put it here. Okay, and you see the results. Okay, you realize that the p-value is the same. It's identical p-value. In fact, the t-statistic is also the same. That's why I give you a p-value the same. Okay. So, conclusion. All right. That is how you do a one sample t-test, which also makes it that a paired t-test is really a one sample t-test. So how do we use one sample t-test most of the time? Okay. In my experience, we use one sample t-test, especially for quality controls, QC. For example, like what? Let's say if you are working in a production line, okay, you want to see, for example, you say that, let's say the label on a cup of others ice cream says that it's 60 grams per cup. Okay, you want to check whether is this true, so you buy, let's say, 10 cups and find and check if the average weight equals to 60 grams. This is how you do a one sample t-test. All right. Just if you do that, then the dummy instead of 0 will be 60 because you are looking at for 60. Okay, so that's how you do your paired t-test and one sample t-test. Okay. All right. Now there's actually a few useful tools in Excel. I will just briefly show you this thing called pivot table as well. Okay. So this will be the last part. I'll show you a bit of pivot table because pivot table allows you to pull out information fast enough. Okay. Then on Monday, we will go through your regression. Okay. So that you can all go for class our practical. So let's say we highlight the entire page. What is this thing called pivot table? It's actually quite useful. Pivot table, let's say you click on insert pivot table, you select the range, you go to a new worksheet. So pivot table is for you to pull out information fast enough. For example, I can say that location. So I want to split by location. I go take the location, go to rows. So I have two locations, Buckingham and Louisa. Okay. I can then take, for example, the age. Age goes to my values. Okay. So in this case, I can actually change, click on this arrow. I can change the field value settings and I can change it to average. This gives me the average in my data set, the average age for those in Buckingham is 47.2 years old. Those in Louisa is 46.7 years old. So it gives me a summary statistics as I want it. So remember Buckingham and Louisa, I have gender. I can even go to Buckingham, male, female, Louisa, male, female. I just take the gender, pull down to another row. So now I have Buckingham, average age for female, average age for male, and so on. I can have different values as well. I can have the average cholesterol level. So I go to values, we give you the next column. I can change it to average and find out what is the average cholesterol level. Okay. So this is actually very useful. Now, if I want males and females, I can even have body frame as well. Correct? You can have small frame, medium frame, large frame. I can pull down the frame and go to the next one. Now I have the frame. Okay. So sometimes we pull out so many, we want to see, okay, how many males are actually large frame in Buckingham. So it's fine. I can just take the age again and go on top. Instead of sum of age, I just go to count. So that gives you a number, the count. So basically, I have in Buckingham, I have 32 females with large body frame, 51 with medium body frame, and 30 with small body frame. Altogether, Buckingham, there is actually 113 females in my data set and so on. And their average age is this, their average cholesterol is this, and so on. Okay. So you can use pivot table to get a lot of information. So just play around with it. All right. So this is your pivot table. Okay. So far, okay. Okay, so we'll end here for today. Next session on Monday, then we'll go through your regression because I don't want to overload you. I will send this to the group chat. All right. So that's all for what we have today. Okay, so before we get started, right, just want to talk about tomorrow's online assessment. So remind me, these are the two topics that was tested in the online assessment too? So medical microbiology and cellular pathology, correct?
Yes.
Okay, so basically immunology has not been tested. So minimally, what you will expect is tomorrow it should be immunology, hematology, and transfusion science. Okay, so these are the three, the blue ones should be tested, but I cannot confirm whether are the rest tested or not. So I just want to flag it out. Okay, as much as possible, we are trying to get marks for you to get your cellular pathology, but this argument is not going to work the next time. Okay, so
Okay.
that's the most important part.
Thank you.
Okay, so with that settled, we can continue with what we want to talk about today. Okay, so the last session we actually talked about how do you do histograms, how do you do your what is this, descriptive statistics. So let me just rename this. This is your descriptive. And we talk about your Ttest. So remember Ttest, ANOVA is actually equivalent to your one-way ANOVA is actually equivalent to Ttest assuming equivariance. All right. So we also talk about your one samples test. This is your two samples test. Okay. So talk a little bit about how to use this thing called pivot table. So with that, we want to do the next part, which is very important, called regression. Okay. So we want to do this thing known as regression. Regression is essentially your research question is really asking, is one variable related or one variable correlated with another variable? Correlation, what is the relationship? A relationship, we are actually looking for an equation. Okay. So for example, in your diabetes data set, you find that there's two blood pressure, BP1 and BP2. Okay. S represents systolic blood pressure, D represents diastolic blood pressure. So sometimes a patient, when it comes to a clinic, after taking one blood pressure, if it's high, too high or something like that, for example, 190, 160 or so, the patient is usually advised to go out of go and take a rest first for 15-20 minutes, come in for the second test. Maybe he's just too nervous, or just walk in or something like that. So we want to say, is there a difference between the first systolic blood pressure and the second systolic blood pressure? Okay, is there a relationship? All right. You should know what is diastolic blood pressure, what is systolic blood pressure. Okay, what are they measuring? Okay. So let's say we take these two and we put it here. Okay. So our question here is there a relationship between the first and second systolic blood pressure? So in order to remove, you have to remove all these empty gaps, those that without the second blood pressure. So let's just do a sort. And what we do is just sort by second blood pressure from largest to smallest. Okay, and we go all the way to the bottom. So the rest is we can remove them. They do not have the systolic blood pressure. Okay, so for regression, we can again use our data analysis tab. And we go to this called regression. Okay, so regression, skip everything. Okay, we want to say that is the second systolic blood pressure. That means is there a second? Let's say the Y is the second systolic blood pressure, the X is the first systolic blood pressure. Okay, is there a relationship? So we go to Y, this is the second systolic blood pressure, and X. Okay, let's do this first. So in this case, what is our null hypothesis? Our null hypothesis is that there is no correlation. And no correlation means that your Pearson's correlation coefficient equals to 0. Okay, alternate hypothesis. There is a correlation. It means that your Pearson's correlation, which is your R, is not equals to 0. Negative and positive. Okay. All right. So in this case, let's go back. Since our Y, let's say our Y is the second systolic blood pressure, our X is the first systolic blood pressure. All right. So we click on the labels because we highlight the labels as well, and we look at the output. So output, let me put it in D1. Output, put it in here. Okay. So it comes up with a few interesting tables. Okay. The first is what you need. This is actually the regression statistics. Okay. It doesn't give you the R, it gives you a multiple R, which is close enough. So this is taken as the R result. R square is just 0.88 square. Okay. So this is R square. So is there a correlation? There seems to be a correlation, but is there a significant correlation? Okay. For that, you look at something quite interesting called ANOVA. So this significance P is the P value. Okay, 2.16 E times 10 to the power E minus 646 means that is 2.16 times 10 to the power of minus 46. So this is the S statistic, which means that there is a strong correlation. Okay, the likelihood that there's no correlation and getting this result, it is 2 times 2 times 10 to the power of minus 46. So there's actually a very low probability. Okay. So based on this, we say that there is a correlation. Basically, we reject the null hypothesis, say out the hypothesis. Then what is here is quite interesting as well. The next table tells you what is the correlation. Okay, remember our BP2 is your y-axis, your BP1 is x-axis, which means that you can write your BP2S equals to, this is the correlation coefficient. Okay, highlight this word, it's called coefficients. It means that this is the equation. This is a coefficient for BP1. It means that BP2 is 0.924554 of your P1S. Y-intercept, the y-intercept is 8.980524. So this is the equation, basically, between the two coefficients, between the two variables. Okay. And for each one, it's actually quite interesting to test. It actually asks for, is this coefficient for the first systolic blood pressure equals to 0? Okay. So here is, you base it on your y equals to mx plus c. statistics, we tend to write as y equals to beta 1 x 0. So what is these values here trying to say? These values are asking for the null hypothesis. And just put this. Okay. You are testing the null hypothesis that beta 0 or y-intercept equals to 0. Here the null hypothesis is beta 1, which is the x-intercept, or no, x variable for x-axis, equals to 0. Then this is the p-value, which means that there is a possibility, 17.8% chance that the y-intercept is actually equals to 0. Okay. So in this case, you fail to reject the hypothesis. Here, for the coefficient, B1 coefficient, you actually reject the null hypothesis, which means that the slope is not equal to 0, and this is a t-statistic for it. Okay, so this is actually quite helpful for you to find out. And it also gives you the upper and lower 95% confidence interval for the coefficient and upper and lower 95% confidence interval for the gradient. Okay. So far, any problem? You can also draw it as a graph if you want to. So this, when you draw it as a graph in Excel, you default this as, this is the x-axis, this is the y-axis. Okay, comes x and y first. So when you draw it as a graph, you draw it as a scatter plot. A scatter plot. Then what you have is at the axis title. So this is the x-axis. Okay. BP1 S. This is your second x. This is your y-axis. Yep. Okay, then if you remove all the grid lines, you can actually go and add the trend line. So you add the trend line, a linear trend line, and we display the equation and the R square value. You find that the equation, the R square value is the same as this R square value. Okay, let me just expand this a bit more. Okay. So you can change the color of the line if you want to. I normally change the color of the line because then it makes it more visible. Okay. So you see, the R square value is the same as what you have in your regression statistics. And the equation is the same as your equation here. It's the same number. Okay. But make sure that what you do is because this is a text box, you change it yourself. So your second systolic blood pressure equals to this times your first systolic blood pressure. Okay, and that will be kind of good enough. Okay, because you really have to change axis, the names of axis. Okay, so far, this is how you can draw a graph and get your results as well. Now, so far, any problem with regression? Okay. Now, anyone actually kind of find it a bit weird and interesting why they give you ANOVA here? Anyone find that this is a weird sign? Why do you get ANOVA table? Or let me ask you another question. Is there a relationship between ANOVA and regression? Okay, and so by instinctively, how many of you think that there's a relationship between ANOVA and regression? Just raise up your hands. Just want to see how many people. Just give your hands up if you raise up your hands already. Anyone? Or you never even thought about that before? That is there a relationship between ANOVA and regression? Okay. Now, since you've not thought about that, doesn't matter. What I'm going to show you is ANOVA and regression are actually the same thing. Okay? When you do a fair bit of statistics, you realize that there is something about ANOVA and regression. But what I'm going to tell you is ANOVA is regression. Okay, that may come as a surprise to you. Right? Say that ANOVA is regression. Yes, this is actually very surprising. ANOVA is regression. So let's look at our two samples test. Okay, remember we talked about this. Is there an average? Is the average cholesterol in male equals to average cholesterol in females? And we do that, right? Okay, let's copy out this ANOVA table. Okay, let's copy out this ANOVA table, and for us to see the results. Okay, let's see what we do. Just put it here. So we have the ANOVA table here. Okay, and originally our question is really this. Is there a relationship between the average cholesterol in male and average cholesterol of females? Okay, why not we try to repeat this whole thing in a regression format to show you, do I get the same results? Okay. So I have cholesterol for males, cholesterol for females. Let's go back. Cholesterol and gender. So let me just paste it here. So what I have to do is that I have to code the gender as a variable, as a dummy variable. So I insert to ask whether is it female. So if it's female, then I put 1. If it's female, if it's male, then I put as 0. That's what I'm trying to do. Either female, yes or no, basically. Okay. So what I'm going to do is I'm just going to use a if statement. If the gender equals to female, then it is 1, otherwise it's 0. Okay. So that will solve my problems. Okay. So it's just this equation. Okay. So if it's 0, if it's 0 means not female, then it should be male. Okay, and so on. So far, okay. Then let me hide this. And I do a regression. Okay. So I do a regression. Basically, what am I doing is, can I, okay, doesn't matter. Let me just show you how I do a regression first. I do a regression, and I find that my Y range, I use cholesterol. Oops, my Y range, I use cholesterol. Hopefully I get this right because I seldom do this myself. And my X range, I use the gender. Okay. So I put my data labels, and my output, I put that in M0. Okay, I click OK. What do you see? You realize that the significance p-value is the ANOVA p-value. The F statistic is the same. So actually, ANOVA is regression in this aspect. Okay. People always say that ANOVA and regression is two sides of the same coin. It's not two sides of the same coin. It is the same coin. Okay, you can use regression to simulate ANOVA. So this is a very important concept that you should know to help you in your statistics life. Okay. Any problem with this? I'll give you this whole document after that. I'll just send to Saifu, and then Saifu can send to the rest of you. Okay. So the last thing what we want to do is this test known as chi-square test. Okay. So chi-square, what I'm trying to do is I'm trying to do a research, and I'm saying that there is, okay, say that the body frame of males are equal. Means that the proportion of large body frame is actually 1/3. The proportion of medium body frame is also 1/3, and the proportion of small body frame is also 1/3. Okay, that's what I'm trying to say. Okay. My null hypothesis is that portions frame are equal, or rather is equal. My alternate hypothesis is the proportion is not equal. So in order to do that, we have to have a chi-square table. So we have observed versus expected, large body frame, medium body frame, and small body frame. So where do you get this data from? It's quite simple. We get it from our pivot table. So we have the large body frame, small body, and so on. So large, medium, small, we just generate a pivot table to get it. Okay, and here they observed large and small. So we need a total. Total is the sum. So the expected, if it's 1/3, we just take the total, divide by 3. Okay, so equals to 6. Expected can have a decimal place, it's no problem. Okay, and because it's 133, right? It's a recurring decimal, so it doesn't matter. It's fine, no problem with that. Okay, then what you do is, let's see, in your data analysis tab, there is no chi-square test here. Okay, so chi-square test, you can only find the p-value. The p-value for chi-square test is just chi-square. You do a chi-square test. Actual range is the observed range, because the other one is expected range. Okay. And this is your p-value, which means that there is about 0.4% chance that the proportion of body frame are equal, and you get this result. Okay. You can say that since p-value is less than 0.05, you reject your null hypothesis. So that you accept your alternate hypothesis. Okay, I'll say that. Hence, you accept your alternate hypothesis. Therefore, the portion, so you explain alternate hypothesis again, of body frames are not equal. Okay, so chi-square test is very simple to do, and it's a very useful test. You do chi-square test for genetics, for a lot of other things as well. Okay, any problem with this? With chi-square test? Any questions? Okay, so the next question that I'll ask you is, must we always use count? So this is a question, for chi-square test. Must we always use the count or the frequency? What I'm trying to ask is, can we use percentage instead? Do you think you can use percentage? That means I convert all these to percentages. Anyone? Anyone?
Yes.
Yes. Okay, so you say that you can use percentage. Okay, so let's try, because the reason why I ask this, right, is that I do know of stats professors that tells me you can use percentage. Okay, but me, you can quote me, Maurice says that never use percentage. Never. Percentage can give you a wrong answer. Okay, percentage can give you a wrong answer. Seriously, I have met with I've talked to statistics professors near their retirement age, and they still insist that I can use percentage. I will show you that you cannot use percentage. Okay, so let us do a simulation. Okay, let us just say that reality. Okay, the reality is that we want to look at the number of coffee and tea drinkers. So the reality is 51% drinks or prefers coffee. It means that 49% prefers tea. Just do it. Okay. We want to test the research question. Is there equal preference of tea versus coffee? Which means that my null hypothesis is that there is equal preference. The null hypothesis is that there is unequal preference. Okay, so let's just do a few tests, and we say that if we use percentage, we say that n equals 100. This is by percentage, right? Because 100 means 100%. So let's try. If n equals 100, we have our observed versus our expected. Okay. And we have coffee versus tea. Okay. Because we expect equal preference, so out of 100% or 100, it's only 50, 50. But our actual observation should be in reality, so should be 51 49. Okay, and we do a p-value or chi-square test. Okay, actual range is range here. No problem. We accept. Our conclusion is we cannot reject null hypothesis, so we accept. We conclude. We say that there is equal preference. Okay, so let us try the next part. So remember, here is you are taking the percentage. Okay, n equals to 100 means using percentage. Remember that. Okay, I should not highlight this. Okay, in fact, this line is quite important. So I'll highlight a different color. Okay. So why not? Let's say if you are very energetic, you do 1000. Okay, have your observed and your expected as well. Also have coffee versus tea. But because you have 1000, your expected will be 500, 500. Now it's 51% versus 49%, so it's actually 510 versus 490. Then let's look at your p-value. The p-value will be identical. Let's look at see what happens. Let's go test actual. See, the p-value is actually different. So because the p-value is different, the sample size actually affects the statistic. So although it still will conclude equal preference. Let's say that you are now super energetic and you do more. Again, and instead of 1000, you do 10,000. You survey 10,000 people. Here will be 500, 5,000, 5,000. Okay. Observed will be 5,000. 51% of 10,000 is 5,100. Here is 4,900. Look at the p-value. It drops to below our threshold. So you conclude unequal preference. If you use percentage, whether you are surveying 1,000, 10,000, 100,000, you will still go back to just this alone. Okay. Very important, huh? Chi-square is sensitive to sample size. The sample size is the count. Therefore, always use the count or frequency instead of converting to percentage. Okay, if anybody in future tells you that you can use percentage, please show them this example. You cannot use percentage, you have to use count. Make sense? Even worse, there are some people who can tell me that you can even use proportion. What happens if you use proportion? Proportion means you take this, right? Proportion means that n equals to 1. And here is 0.51, 0.49. Here is 0.5, 0.5. See? We say that n equals to 1 means using proportion or ratio. Your conclusion will be wrong again. So always use count or frequency instead of converting to percentage, or worse, okay, please show anybody this example if they tell you otherwise. All right. So actually, that's all that I have for today. Just to give you a brief revision, basically a 1.5 hour revision for the last 2 sessions of everything. Okay, these are the important statistics that you need to know. There's a lot of other statistics that you have to know or you should know, but it's not within your syllabus. Then when you need it, then, well, find help. Okay. Let me save this. Any problems? Okay, if nothing else, then that's all for today. Quick session. Okay, so remember for the OA tomorrow, we may not know what comes out. Okay, all right, that's all for today. Have fun.